Hi friends, welcome to the lecture of Advanced Discrete Mathematics. In last lecture, we have seen what is a post. What are the posits? Now we have to see what is a product order and lexicographic order. First, first see what is a product order. Definition for elements S, comma S dash belonging to set S and T comma T dash belonging to set T. The product set set S cross T defined by ordered pair ST besides S dash T dash if and only S precedes S dash in S and T precedes T dash in T where ordered pair ST and S dash T dash are in S cross T and it's called product order. Okay. So product order is nothing but for any S dash belonging to set S, partial ordered set S and T dash belonging to T. The product set S cross T, which is defined by ordered pair ST precedes S dash T dash if element S precedes S dash in S and T precedes T dash in T, where S T and S dash T dash are the ordered pairs belonging to Cartesian product S cross T are in Cartesian product S cross T. Cartesian product X cross T and is called product order. Let us take one theorem depending on the definition. Sorry, this is the relation defined on Cartesian product S cross T. Therefore, on S there is a different relation and on T is another relation, that is S precedes T precedes product of T dash. Now let A precedes 1 and B precedes 2 are posits. Then A cross B with a relation precedes is a posit where the partial order defined by A comma B precedes A dash B dash in A precedes A dash in 2 and B precedes B dash in. So here we have given two posits A and B and we have to prove that its product A cross B, that is Cartesian product A cross B, is also a posit where the relation defined by AB precedes A dash B dash if A precedes A dash in A and B precedes B dash in B. Let us prove it. Here we have to prove that A cross B is a poset with this relation. Okay. So now we have to prove that this relation is closed under the reflexive, antisymmetric, and transitive property on the set A cross B. First, let us prove A cross. This relation is closed under reflexive. That is, any ordered pair belonging to this Cartesian product is related to itself. Okay. Now, AB precedes AB. But here define that AB precedes AB if A precedes A dash in A. Sorry, AB precedes A dash B dash if A precedes A dash in A and B precedes B dash in B. Then from this definition, A precedes A in A and B precedes B in B, which is from given definition of our product set. Okay. Now A precedes A in A, but we know that whether now we have to check which is from definition of product set. Now we have to check whether A precedes A in set poset A. We know that A is a poset. As A is a poset, then this relation is a symmetry. Sorry, reflexive, antisymmetric, and transitive on A. Therefore, A is related to A itself since it is A is reflexive. Therefore, this one is true. Similarly, B is related to B itself since B is again a poset. Therefore, which implies AB is AB precedes AB, which implies this relation precedes is reflexive. Okay, now second one. Let AB precedes A dash B dash and A dash B dash precedes AB. Now, from the given definition of product set, let us write this one. AB precedes A dash B dash, which implies A precedes. Let us write first where this A dash are belonging to. As AB precedes A dash B dash, then A and A dash are belonging to set A and B and B dash belonging to set B. Where A comma A dash belonging to A and B comma B dash is belonging to B. But we know that A and B are two posets. As A and A dash are belonging to A, then if A precedes A dash, let us write first from given definition. From given definition of product order, AB precedes A dash B dash, which implies that A precedes A dash in A and B precedes B dash in B. And also given that A dash B dash precedes AB and A dash precedes A in A and B dash precedes element B in poset B. Therefore, from this A precedes A dash in A precedes A dash and A dash precedes, just take this one as 1 and this one as 2, and A dash precedes A in poset A and B precedes B dash and B dash precedes B in poset B, which is from 1 and 2. From 1 and 2. Since A precedes A dash in A and A dash precedes A in A. But we know that this A is a poset. As A is a poset and A precedes A dash and A dash precedes A, then this A must be equal to A dash. Since as A is a poset, then it is antisymmetric, which implies A is equal to A dash and B is equal to B dash. Since B is also a poset, as A is equal to A dash and B is equal to B dash, then AB precedes A dash B dash and A dash B dash precedes AB is implied, which implies that A and A ordered pair AB is equal to A dash B dash, which implies ordered pair AB is equal to A dash B dash. Since A is equal to A dash and B is equal to B dash, and we know that four ordered pairs are equal if their corresponding elements are equal, which implies the relation is antecedent. Okay. Now it remains to prove that it is a transitive. Third one. Let AB precedes A dash B dash and A dash B dash precedes A double dash B double dash. Now, from given data, where A dash A double dash is belongs to A and B dash B double dash belonging to set B. Again, from given definition, AB precedes A dash B dash, which implies that A precedes A dash and A dash B dash precedes A double dash B double dash, and A dash precedes A double dash in B. Similarly, B precedes B dash and B dash precedes B double dash in poset B. Here we take this relation since on B, this one is the partial order relation. Okay, now A precedes A dash and A dash precedes A double dash in A, and A is a poset. As A is a poset, then it is transitive. As it is transitive and A precedes A dash and A dash precedes A double dash, which implies that A precedes A double dash and B precedes B dash and B dash precedes B double dash in poset B. As it is B, then it is a transitive. As it is transitive, which implies that B precedes B double dash. Now, as A precedes A double dash in A and B precedes B double dash in B, then from the given definition, A B precedes A double dash B double dash. Then from the definition of transitive property, the relation is a transitive. As this is a relation is a reflexive, antisymmetric and transitive, then it is a, which implies the relation is a partial order. As it is a partial order on Cartesian product A cross B, which implies A cross B with this relation is a poset. Okay, and which is the required result. Okay. The partial order, the partial order is seen on Cartesian product, Cartesian product A cross B is also called a product partial order. A product partial order, and the poset A cross B with its relation is called product posets. Product poset of posets A precedes and B. Okay. If the partial order this with this relation on a Cartesian product A cross B is called a product partial order, and the product and the poset A cross B is called a product poset, which is a product of two posets A precedes A and B. Okay. Now we can extend the same concept the same concept on finite number of finite number of posets. Okay, here we have proved for only two posets, but if we take any n posets, then this result also holds. That is, if a1 precedes 1 comma a2 precedes 2 up to so on an is n are n posets are n posets, then the product set a1 cross a2 cross up to so on cross an with the relation is also a poset where the partial order precedes is defined by is defined by a1 e2 up to so on an precedes b1 b2 up to so on bn if and only if a1 precedes b1 in a1, a2 precedes b2 in a2, and so on. An precedes bn in an. Okay, so here we can generalize or extend the concept of product of partial ordered set on n posets. Okay, now the next point is, what is a lexicographic order? Lexicographic order. Suppose st and s dash t dash b possess then the Cartesian product s cross t defined by ordered where st precedes s dash t dash if either s precedes s dash in s, or if s is equal to s dash and t precedes t dash in t, that is one ordered pair is t, one pair is less than the second ordered pair s dash t dash less than the second pair if either the first entry of the first pair is less than the first entry of the second pair, that is s precedes s dash in yes, that either the first entry in first pair is less than the first entry in the second pair, in the second pair, or if all entries sorry, if first entries are equal, if first entries are equal but second entry of the first pair is less than the second entry of the second pair, but second entry of the first pair is less than the second entry of a second pair, of second pair, and and ordering of this type is called lexicographic order or dictionary order. Okay, if suppose we have given two posets yes and t, then the Cartesian product of these two posets yes and t, that is s cross t, defined by st precedes ordered pair s dash t dash if either yes precedes yes dash, that is the first entry of the first pair is less than the first entry of the second pair, and if the first entry of the first pair is equal to the first entry of the second pair but the second entry of the first pair is less than the second entry of the second pair, then this type of ordering is called a lexicographic ordering or dictionary ordering. Okay, now this is for only two posets. Now similarly we can extend this concept on n posets. Similarly we extend on S1 cross S2 cross up to so on cross Sn, where S1 S2 up to so on Sn precedes S1 dash S2 dash up to so on Sn dash if Si is equal to Si dash for I running from 1 to up to so on k minus 1, and sk precedes sk dash. That is, if suppose s1 cross s2 cross up to so on sn is an Cartesian product, then its element s1 s2 up to so on sn precedes s1 dash s2 dash up to so on sn dash. Here, how will you check whether this first term precedes the second one or not? By lexicographic ordering. If we first check whether the first element of first pair precedes the first entry of the second pair. If S1 precedes S1 dash, then we can easily say that this one is a precedes this one. But if suppose S1 is equal to S1 dash, then we go to the next character, that is S2. Now here we will check whether S2 precedes S2 dash or not. If S2 precedes S2 dash, then the process stops here only. If S2 is equal to S2 dash, then we can again go to the next character, and similarly we can check for all characters. Okay, now let us take one example. check whether ordered first one ordered pair 3 7 3 6 4 comma 8 and second one is 3 comma 9 3 6 3 comma 11 in the product possess whether possess Z cross Z with relation less than or equal to. Okay. Now we have to check whether this ordered pair 3 9 is less equal by 3 11 and the poset 3 7 is less equal by 4 comma 8. How will you check this? From this method. Here, let us take first one. Now we have to check whether this 3 comma 7 is less equal by 4 comma 8. That is for this relation. How will you check it? But first we have to check whether 3 precedes this 4. That is whether 3 is less equal by 4. As here 3 is less than 4, therefore the process stop here only. But in second, we have to check whether 3 9 precedes here precedes is nothing but the less equal relation. That is 3 comma 11. So here we have to check for the first entries in the both the pairs. Here 3 is equal to 3. But the second entry of the first pair 9 is less equal by 11. Therefore, which implies this 3 9 also holds the property. Hence, both the examples are true. Okay. Now, we now define the lexicographic ordering on strings. We now define the lexicographic ordering on strings. Consider the strings. Consider the strings W equal to A1, A2, so on, AM, and W dash is equal to B1, B2, up to so on, Bn. Okay. On the partially ordered set, yes, where K is nothing but minimum of this M comma N. Then the string W, then the string W is less than the, then by the definition of lexicographic order, then by the definition of lexicographic ordering, string W is less than string W dash if and only if A1, A2 up to so on, AN AM precedes B1, B, sorry, some AK, since we have taken K is nothing but the minimum of MM. A1, A2 up to so on AK and B1, B2 up to so on B. So these two strings, in between these two strings, the first string W dash is, sorry, first string W is less than the second string W dash if this ordered pair A1 A2 up to so on AK precedes B1 B2 up to so on BK. If this is not possible, then or if A1 A2 up to so on AK is equal to B1 B2 up to so on BK, where M must be less than N. Then we say that this one, that is string W is less than the string W dash. Okay, now we can apply this idea on the words. Now we use this idea to compute the words, that is, if A is nothing but words A1 A2 up to so on AM, and B is nothing but B1 B2 up to so on Bn, character by character, character by character, passing over, equal characters. Okay, now we have to check which word is first and which word is second in the lexicographic ordering. Okay, now if at any point, at any point the at any point the the A character alphabetically precedes alphabetically precedes precedes the corresponding B character, B character, then B character, then word A precedes B. If all characters, another possibility, if all characters in word A are equal to the corresponding characters in B, corresponding characters in B, but we run out of characters in A before the characters in B. Characters in word B. Then this A precedes B, or then A precedes B. Otherwise, B precedes A. So, if we have to arrange some words in alphabetical order, then how will you arrange the two words? If suppose A and B are two words where A contains M character and B contains N character, and we have to arrange these words A and B in alphabetical order. So, here we have to take the two words, and if any character in A is alphabetically precedes, that is first character in A alphabetically precedes the first character in B, then the word A precedes the word B. If suppose all the characters in A, that is all the characters in word A are equal to the all the characters in word B, but number of characters in A are less than the number of characters in B, then this A is precedes B, otherwise B precedes A. For example, arrange the following words over English English alphabet in lexicographic ordering. Okay, lexicographic ordering. And which are the words? Words are nothing but first one is like, second one is life, third one is limitation, and fourth one is limit. Okay, now we have to write these words in alphabet order by using the lexicographic ordering. Okay, now lexicographic ordering on string says that first we have to write the words according to our length. The according to our length. Therefore, like, life, and limit are like and life are strings of length 4. Limit is a string of length 5, and limitation is a string of length 10. Therefore, write according to our length. First one is like, second one is life, third one is limit, and fourth one is limitation. Okay, now let us check which word is first. Like and life. Here in life precedes like. Since according to lexicographic ordering, L is equal to L, I is equal to I, but this F precedes K. As F precedes K, then we have to write first word as a life and second a life. There, which implies life precedes like and like precedes limit. Okay, since here also L is equal to L, I is equal to I, but this K precedes M. As K precedes M, then we have to write first word as a like. Then we take limit. Now we have to check in limit and limitation which one is the third one and which one is the fourth one. Okay. Now here the string limit is here. The string limit is of length 5 and string limitation is of length 10. Then minimum of, that is K is nothing but minimum of 5 comma 10 M and N, which is nothing but 5. Therefore the word limit run out the characters in limit before the characters in limitation, since limit contains less number of characters in limitation, but all the characters in limit and limitation are equal up to fifth one, but limit has less number of characters than the limitation. Then first we get limit and after that we can write limitation. So this ordering is nothing but like precedes limit, and which is precedes limitation, and which is the required alphabet order of given words. Okay, now there is one theorem. Let S1 precedes 1 and S2
this is 2, to so on. Sn, this is N, B,
chains.
B, change. Then the lexicographic ordering, lexicographic ordering pieces on S1 cross S2 cross to so on cross Sn is also a chain.
So here, given that S1, S2 up to so on, Sn are the n chains, then we have to prove that S1 cross S2 cross up to so on cross Sn is also a chain. Okay. For that, if we have to prove that this Cartesian product is a chain, then we have to prove that any pair of element belonging to this Cartesian products are comparable. Then only we see that the corresponding Cartesian product is a chain, that is a totally ordered set. Okay. Let S1, S2 up to so on Sn and T1, T2 up to so on Tn be distinct elements, be distinct elements means in Cartesian product S1 cross S2 cross up to so on cross Sn. These are the elements of this Cartesian product. Okay. Now, as S1, as this ordered pair is, these two ordered pairs are distinct, then there exists some R such that this SR is not equal to TR. Then only we can say that these two ordered pairs are distinct. As they are distinct, then there exists some R such that SR is not equal to TR. But here, ordered pair SR with this relation is a chain. As this one is the chain, then any pair of element belonging to this set SR are comparable. Therefore, either SR precedes TR or TR precedes SR. Since this SR is a chain and these SR TR are the elements of this coset SR. Therefore, as this is a coset and it is a chain, therefore SR precedes TR or TR precedes SR. Therefore, the elements S1, S2 up to so on Sn precedes T1, T2, T1. That is, if SR precedes TR, then we get S1, S2 up to so on Sn precedes T1, T2 up to so on Tn. That is, these two elements are comparable with this relation. And if suppose SR is not related to TR, but TR is related to SR with given relation, then or T1, T2 up to so on Tn precedes S1, S2 up to so on Sn. So, if we take any pair of distinct elements belonging to the Cartesian product S1 cross S2 cross up to so on Sn, then the elements are always comparable. As any pair of elements in these Cartesian products are comparable, then by the definition of chain, it implies the Cartesian product S1 cross S2 cross up to so on cross Sn is a chain, and hence the required result. Okay. Thank you for watching the lecture.